Yeah, I got it. I'll probably look at it tonight, but the links don't work all.
Okay, welcome back everybody for the afternoon session. So the first talk of the session is by Don Marolf, Gravitational Path Integrals for Fun and Profit. Thank you.
So this is admittedly, oh, sorry. I'll have to switch it on. There's an on right there. Yes. Yeah. Is it on? Yes. All right, now I'm being recorded. Very good. So thanks. Admittedly, this is one of those titles that I give when I don't know what I'm going to say, because I've been thinking a lot about path integrals for the last couple of years, and so this covers pretty much anything I'd like to do. But in reflecting on what I did want to say for this talk, I thought a lot about maybe the kind of talk that Ted would give, and I thought, okay, Ted would give a talk which does several things. First of all, it would emphasize physics as opposed to details of mathematics. And I said, okay, I can try to do that. And another thing I thought that a talk by Ted would do would be to sort of start at the beginning and build a clean foundation, even maybe at the expense of not explaining the detail of the latest calculation. I thought, okay, I can do that too. And the third thing is I thought, if Ted were going to give a talk on something like this, it would also be beautifully crystal clear conceptually. And I thought, I'm not sure I can hit that bar, but I can at least do the first two. So I am going to give a talk that, as I say, that really explains, I'm going to start by explaining why, from a certain perspective, I've been thinking a lot about gravitational path integrals, and vaguely what I'd like to do about that. And I will allude to some of the more concrete results at the end. This kind of talk, I think, is also good for this audience, because by starting at the conceptual beginning in some sense, I'm going to give a talk which is an interesting kind of mixture of old and new things. I will say some things that could have been said, were said, some of which even by me, some very long time in the past, 30, close to 40 years ago. I don't know, long time in the past, more than 30 years ago. More than 30 years ago, unfortunately. Yeah. But which I think will still be of interest and will even resonate with some of the young people in the audience. On the other hand, the way I'm going to say some of those things is certainly informed by many, many developments over the meantime. So this is an interesting synergy. Okay. So what am I interested in doing really? Well, it's the old story. I'm interested in trying to understand a theory of quantum gravity. And I'm interested at the moment in understanding how one might, as I would say, formulate the theory. What are its general structures, independent of the details? I'm also focusing on what in modern language would be called an effective theory of quantum gravity, where I'm not worried about all the ultraviolet problems. I'll just sweep them under the rug or do something to ignore them for a while. So I don't care whether there are strings, loops, whatever, it doesn't matter to me. We've seen over the years, I think everyone has been clear that something in the description of quantum gravity is interesting even at long distance scales, far longer than the Planck scale. And when I say something is interesting, I mean that theory of quantum gravity is certainly not, a quantum field theory, even on long distance scales. And this black circle is, of course, there to remind us that the obvious thing we've been discussing for many, many years is black hole entropy. And no matter what your perspective is on that, I think one agrees that the Bekenstein-Hawking entropy is not defined by a standard quantum field theory in fixed spacetime background calculation. That interesting things happen in the infrared in quantum gravity that have something to do with that. And although I personally feel like we've made a lot of progress on understanding the black hole information issue in the last few years, I also feel like there are related issues about the structure of formulating quantum gravity in general, even on long distance scales, that we have not completely sorted out. So I'll be talking about that as we progress. Okay, so here's the outline of my talk. I'm going to spend some time explaining why, in some sense, I want to talk a lot about path integrals. I'll then have a brief reminder of what I call successes and failures of Euclidean signature path integrals. I'll give a plug for Lorentzian gravitational path integrals and the way I'd like to treat them. And time permitting, I'll list a few results to guide you to further reading. So that's the plan. All right. So why study path integrals? Well, one answer is why not? Or a better answer is let's look at the alternatives and see what issues they might have and what might lead us to think about path integrals in detail. Or in other words, even if you don't like the idea of a path integral because path integrals are hard to control in terms of rigorous mathematics, there might be some pieces of inspiration you'd like to gain by thinking about path integrals that could inform other kinds of approaches. Okay. So what else could you do? Well, you know, the mathematically cleanest way to make a quantum theory, at least in my opinion, is to do the following. You find an algebra and study its representations. So for a theory of gravity, you might imagine you could formulate a theory of quantum gravity by identifying some algebra of gauge invariant operators and then studying it. Once you've got the algebra, it ought to be a clean, if complicated, mathematical problem. Of course, the issue in trying to attack quantum gravity this way is the question of what algebra do you study? Where do you begin this question? And it's worth saying this in a little bit more detail. So, okay, where do you start? What is the algebra you're looking at? And in particular, I guess I'd like to dwell on this point. Oftentimes, we quantize theories by considering the classical system, constructing some sort of Poisson algebra, and then imagining that there is some consistent deformation of it that leads to some quantum theory. In the context of gravity, I find that particularly problematic, the idea that you would construct the algebra of gauge invariance using just the classical equations of motion, and then quantize that for the following reason. The issue is that, well, we want the algebra of gauge invariance. Of course, we usually think of gauge invariance in gravity in a covariant way in terms of diffeomorphisms. But to say that, you know, we have diffeomorphisms in space and in time. In order to say that diffeomorphisms in time are gauge relations, we have to first have some idea of what operators we might be relating at different points in time. In other words, we have to somehow have a notion of time evolution to talk about diffeomorphisms as being gauge. And where does that come from? Well, again, if we're just solving classical equations of motion, then any notion of time evolution we use to define this algebra is going to be based on classical time evolution. Not such a bad idea necessarily, but a real concern that I'm going to dwell on is that if you first solve the classical equations of motion and then quantize the theory, you'd miss out on important quantum mechanical phenomena like quantum tunneling. So let me now make this concrete, because I'm sure this sounded like very abstract, no one's quite sure what I'm saying, but let me just illustrate this in Newtonian particle mechanics. Suppose I give you the theory of a Newtonian particle. Classical mechanics, standard kinetic term, coupled to a potential. I want a potential that looks like this. It's got some big, narrow wall here in the center, which is arbitrarily high, so that the classical dynamics completely separates into a space of solutions on the right and a space of solutions on the left that don't mix. Then if I look at the covariant phase space or the space of solutions, and I look at some Poisson algebra defined on it, if I take any function on that phase space, which is supported on the left side say at some time t equals 5, and I ask how such functions on the phase space are related to functions supported on the left side at t equals 0, well, the answer is that there's some straightforward relation. This notion of which side of the wall you're on is preserved for all time. So things on the left side at t equals 5 are also on the left side at t equals 0. There's no mixing between left and right. On the other hand, what we all believe is the correct quantization of this system is to allow tunneling across this wall. And if the wall is infinitely high but sufficiently narrow, then even in the WKB approximation, you can see that the tunneling coefficients are non-zero across the wall. And so, in fact, the two sides do mix. And so I just want to emphasize that this kind of issue is one that I worry about if we try to trust the classical theory too much in terms of defining the starting point for our quantization when we use time evolution. So I hope that at least makes this worry seem somewhat concrete. So I think that I think it's at least difficult, well, for more than technical reasons, I think it's very difficult to imagine first constructing a classical algebra of gauge invariant operators and quantizing the result. Of course, one could think of this as some order of h-bar correction. One can think of it as deformation of the classical algebra. But once you allow arbitrary deformations of a complicated algebra, now you're in the land of who knows what we're doing after all. So I think this is maybe that useful place to start.
Like the canonical quantization should work fine. Particle fine, right?
Yeah.
Is there an actual puzzle here, or
no? There are two things you can do. You can quantize. You can start with the algebra, the equal time algebra, and you can quantize it in the normal, straightforward way, and that works great. And then you say, oh, one of the things in the equal time algebra is the Hamiltonian. I will use the quantized Hamiltonian to define time evolution. That works great. What I'm saying is more complicated is if you tried to study the entire covariant phase space, or thinking of it as the space of solutions, then that algebra does not lead you in a straightforward way to the usual quantization. Now, go ahead, Bob.
Well, I was just gonna say, I mean, that seems more not a problem between classical and quantum, but between particle and field theory. You started with a classical field theory with that potential, but there's still classically tunneling, and if you set up the field theory phase space, then the quantum field theory would just mirror that with no changes there.
Very true. I love this discussion. So I'll have some deeper side. Of course, it's also true that if you consider a classical field theory in general, there can be structures like this that can separate one behavior from another, and there can be some additional analog of quantum tunneling. And so I think if you applied what you just said to gravity, you'd be advocating something like what's called the third quantization approach to gravitation, which would all be fine with me, but I wanted to make that point. Okay. Because of course, quantum field theory is just different than the theory of a finite, or quantizing a field theory gives you something different than quantizing the Newtonian theory of a finite number of particles. Different story. Okay. So this is one thing which is at least complicated and hard, and we'd like to get some inspiration about where to even begin this from something else. Oh, there's also this annoying thing. We all do worry about the fact that things are kind of funny in the ultraviolet with gravity. So is the real gauge symmetry of the theory really at the quantum level going to be just smooth diffeomorphisms, or is it going to be something else? I don't know. All right. So that makes this a hard starting point. Let's try to do something a little bit different. Let's try to refine that. From my perspective, the the strength of Dirac's approach to quantizing gravity is that it gives us at least a handle on some of the problems I just mentioned. So instead of, in Dirac's approach, instead of trying to first identify the algebra of things that are all the fully gauge invariant operators and quantizing it, what he really did is said, let's define a set of objects, what I'm going to call an algebra, that are still gauge dependent, on which the gauge transformations act non-trivially. Within that algebra, we can identify certain things as generators of gauge transformations. In Dirac's case, these were the constraints. And then you say, okay, if I quantize those things, it gives me a quantum notion of what the gauge transformations are. And I can then pick out from this quantized algebra of gauge-dependent things the gauge-invariant subalgebra. Okay. So that gives us a little bit more of a handle on things. But there are still some very interesting general conceptual concerns and questions about what to do that I think are very interesting. One is, okay, so in a canonical approach to this, the generators of gauge transformations are constraints, and they're this traditional constraints of GR. So let's think about what the Hamiltonian constraint in particular does in general relativity. And it has this really annoying property, which is that in the way we usually describe it, the flow on phase space generated by the Hamiltonian constraint is not complete. Instead, you can start at some nice place in phase space, and in finite flow, you can end up at the boundary of the phase space. This is the usual example of that, or a standard example. This is like saying that you take some universe, like k equals +1 FRW, and you evolve it under a finite amount of evolution by the Hamiltonian constraint, i.e. you evolve it forward a finite amount of proper time, and you reach a singularity, something that by definition lies at the boundary of your phase space. So there's this annoying issue, if you try to follow this approach, that the constraints that you'd like to quantize, you'd like to make them into some kind of actual well-defined operator in order to really implement the Dirac approach, well, at least there are some extra ingredients you need to make it an operator. You need some kind of boundary conditions over here to make the constraint nice, maybe to make it essentially self-adjoint or whatever your favorite property. So this is an annoyance, and is a place where it appears that additional input from some notion, well, that some additional input is required that we just don't have. We don't know what to do from the classical theory. What I want to emphasize in this talk is that this was a story about incompleteness of flows for the classical Hamiltonian constraint, really, because this is about classical solutions. The quantum constraints are even worse. So why are the quantum constraints worse? Well, the quantum constraints are worse precisely because of tunneling type phenomena. It turns out that there are parts of the boundary of phase space which are shielded from this problem, basically due to things like potential barriers, due to these energetic constraints. If you start on the constraint surface where the energies are sort of zero, then there are parts of the boundary of phase space that it's hard to hit. The trajectories naturally veer away. But if you really tried to quantize that constraint, you'd have to think about issues that are very much related to ideas of quantum tunneling. And if parts of the boundary are shielded by a potential, you might still have a non-zero amplitude to sort of tunnel to the edge of the boundary. And then you'd have additional boundary issues to think about. And so here's my pictorial example of what I'm trying to say to make this more concrete. Imagine taking a single spherical universe and considering deforming it. So view each slice of this picture as just a deformation of that spherical universe. So one thing you could do to a sphere is to have it pinch off in the middle so it looks like two spheres touching. That's what this cartoon is supposed to indicate. Okay. if you take, so you have some phase space associated with universes of S sphere cross time topology. And if you sort of pinch off the sphere at the waist, you get a singular configuration that lies at the edge of the phase space. And this is something that doesn't happen in classical evolution in GR. So it's not exactly the same kind of problem about flows in the classical phase space. But I claim that it does, or at least it could, without having put extra input in, as opposed about boundary conditions at the edge of phase space, without ruling it's out by fiat, you might say, it's something that can happen due to quantum tunneling. And how do I know it can happen, or how do I know it's at least a concern? I know it's a concern because, well, in the WKB approximation, studying quantum tunneling is the same as finding solutions to the Euclidean equations of motion. It's just a true fact about studying the Hamiltonian dynamics. It's Hamilton-Jacobi theory. Okay, it has nothing to do with whether you believe in path integrals or Euclidean field theory. Fact. And there certainly exist solutions to the Euclidean Einstein equations that look like this, where you can cleanly separate the universes into two pieces. So I claim, without having written down all the math and without being as clear in a talk as Ted would have been, that this indicates that if you were studying these constraints at the quantum level, you'd have to worry about what to do at boundaries of phase space that look like this in order to make the constraint a well-defined thing, in order to understand what kind of quantum flow it would generate, or in order, if you might say, in order to exponentiate the constraint operator and make it into some bounded operator that you could then try to study its impact on this algebra.
The argument something like the saddle you wrote down has finite action, therefore the barrier isn't strong enough.
That is precisely the argument. Yep, that is the argument. The barrier has the distance, the traversing from a finite point to the boundary gives you finite Euclidean action, and that gives you some suppression, if you like, of the wave function, but not enough to render the details insensitive to boundary conditions at the boundary. So I claim that this is something which is obviously where we can use Euclidean gravity to directly give us insight into at least things that are issues for operator studies of Lorentzian gravity. And furthermore, this picture also suggests something very interesting. And as I said, if you sort of slice this at the right place, the lower slice looks like this, but the upper slice looks like, okay, I start with two spheres that kind of touch, and maybe there's some singular curvature where they're touching, but then they separate and they go their own ways kind of merrily and happily. So I'm going to cheat slightly and say that that's like saying that on the side where there are two universes, again, there's some finite amplitude to reach a boundary. And of course, what this picture shows is that there are at least some contexts where those two problems fit nicely together. So this is the way that I like to think about, or I should say that I would like to think about, quote, topology change in general relativity, in quantum gravity. I'd like to think about it as there are two, classically, we think that there are two different phase spaces, the two universe phase space and the one universe phase space. And that there are things that I probably shouldn't have drawn this way because it's not actually the flow of the classical Hamiltonian constraint. But there are, if you like, tunneling processes from where you could start here in the depths of the one boundary, one universe phase space, and you could tunnel to the boundary. And you could also tunnel from the depths of the two-universe phase space to its boundary. And there's at least a suggestion that those two things fit nicely together. There's a suggestion from thinking about Euclidean gravity that, in fact, okay, so I've just argued that you need some boundary condition here and here. And there's a suggestion from Euclidean gravity that a nice set of boundary conditions might be to simply glue together the boundary of the one universe phase space with the boundary of the two universe phase space. And to think about the constraint as acting in a way that mixes the two. So that's the way that I would like to think about ideas of topology change in quantum gravity. And this is perhaps motivation for thinking about path integrals and perhaps even Euclidean path integrals, or at least the Euclidean paths in a way that might define that sewing together. So this is the kind of thing I would like to be. So while I haven't explained in detail, well, I don't know in detail exactly what I'd like to do here, I would like to be inspired by thinking about even the poorly defined Euclidean path integrals to figure out, whoops, how to do this kind of thing in a useful and nice way. Steve.
Doesn't this give you an awfully big boundary? I mean, if you're thinking about topology change, there are an infinite number of three-manifold topologies that you can all connect to the sphere. I'm not even sure that they're classifiable. In 4 dimensions, they certainly aren't. Are you saying that you want that to have a quantum theory of gravity, one has to consider all possible topologies, or do you have some selection rules in mind?
For the moment, I'm saying, yes, let's put them all together. Seems natural. And whether they're classified, I mean, in 4 dimensions, they're not classifiable. Whether they're classifiable in 3 dimensions, I think they are, but it doesn't really matter. Because, you know, maybe this is actually an advantage in higher dimensions. Maybe it's easier to study the thing when they're all sewn together in some way than trying to sort out one from the other.
Okay, maybe.
Okay. I don't know. But yes, that is the idea. Okay.
There's also arguments that are converged. That there's like too many.
Oh. Yeah. Ask me that later. That's when you try to sum over them, right? Okay. And that is certainly an issue, but as I say, ask me that later. Let's do some simple things now. All right. So this is why I find I wish to be inspired by thinking about path integrals. I want to understand how to do things like this. I like to understand what the effect of this kind of sewing together of different classical phase spaces, I like to understand what the effect of that is on other kinds of physics. And so in particular, if people have used Euclidean path integrals to do various interesting things. This starts off, of course, long ago with the Gibbons-Hawking calculation of the semi-classical partition function. And there's actually a long chain of developments that led from that to calculations a few years ago of the so-called page curve for an evaporating black hole using replica wormholes. It's very much the same in spirit as the Gibbons-Hawking calculation, but more complicated. And there are other things that have been done more recently. So these are things that have been done using Euclidean path integrals. They are been done, they say, calculations. These, it has at least been, well, these are interesting pieces of physics that people have extracted by manipulating the so-called Euclidean path integral, put it that way. I will count all of these as successes because they're interesting. However, a point I wish to emphasize, I think everyone in this room knows, is that the Euclidean path integral, as is often discussed, is, of course, completely ill-defined for various reasons. I want to stress a reason that has nothing to do with ultraviolet physics and is all about infrared physics. It's the usual old conformal factor problem. So this is the one side summary of that. It's often useful to remind people that Euclidean spheres have negative action. And so if you have a whole bunch of spheres which are disconnected, then obviously you've got a large negative Euclidean action proportional to the number of spheres. And in high enough dimensions, you can smoothly join one sphere to the next with a tiny neck at some tiny cost in the action. And so you can put all these things together into a single connected manifold, which has, again, very large negative action in the limit where the number of spheres goes to infinity. And you can do this with sort of finite size spheres that are not Planck size. So this has nothing to do with ultraviolet effects. It's just an issue for the Euclidean path integral because the Euclidean action can be unbounded below. And somewhere up here, I put in a cosmological constant just for fun. But if your spheres are the right size, you get this effect independent of the cosmological constant. So the formal Euclidean path integral, even at a very formal level, has this well-known problem that if you imagine that you're integrating over all real Euclidean metrics, the integral just diverges because e to the minus s becomes very large. Oh yeah, 10 minutes. Okay, that's fine. So what do you do about that? Well, Gibbons and Hawking told us, and Perry told us many years ago, that what you want to do is to choose a different contour instead of integrating over the real axis. All sounds good. Question then becomes, which contour do you pick? And I just want to make this very concrete in case it's not obvious to people why that's an issue. What we actually do with the path integral is we use the semi-classical approximation. We find classical solutions to Euclidean gravity. We find a bunch of them, and then we say, I like that one, and I like that one. And the question is, why do you like this one or that one? Okay. Well, a good answer would be, oh, I defined the Euclidean path integral with this contour through the space of complexified Euclidean metrics. And I can study how to deform that contour, and it passes nicely through this saddle point and not nicely through that saddle point. But of course, and that would be a conceptually reasonable framework, and it would be mathematically valid to the extent the path integral makes sense. But of course, it has the problem that whether or not this prescription says that we like a given saddle depends on which contour we use in the beginning to define the path. So here's my just cartoon example of that. I'll just do this as a one-dimensional. This is a complex plane in one variable. I've made up some action so that e to the minus s is my integration variable. This is supposed to be a color map of the magnitude of e to the minus s, where I've just made up some analytic function to use for this. And the color map is that red is large integrand, so the integral is trying to diverge. Blue is small integrand. So here's an example, not completely random example, but an example of a function that I've made up. This lavender thing is a branch cut, which is why things look discontinuous across it. And in this particular object, so you can see the magnitude of e to the minus s plotted here in colors. And because the function is analytic, that determines the phase contours as well. The phase contours are these dashed lines. If you stare at this and think about it, you'll realize there's a saddle point here at the red dot. And you'll realize that there's a steepest descent contour through the saddle, which is this dotted blue thing. And there's also a steepest ascent contour through the saddle, which is this red thing. Okay. So if I then take that as my function, and if I decide to define my integral as the integral along the green contour, which clearly goes right through the saddle point, then guess what? The saddle contributes and controls the integral. On the other hand, if I decide to define my integral by integrating along this silver contour that goes off this way instead, then the saddle point has nothing to do with the integral. In particular, you can see that the saddle point is more orange or more towards the red side than any point on the integration contour, which means that it's much larger than the integrand at any point here. So in the semi-classical limit, it can't possibly have much to do with this integral because it's just much bigger than the actual answer for the integral. Okay, that's fine. And then one can mumble fancy words about, Picard-Lefschetz and so forth and doing this in higher dimensions. But this is the basic issue, that the contour you choose to define the integral a priori makes a big difference as to what the answer is. All right. So the thing that I've been thinking about for the past couple of years is this, which is not a new idea, that we want to define this contour. Maybe Euclidean techniques are kind of nice, but obviously integrating over real Euclidean metrics, not a good idea. What else can you do? Well, how about integrating over real Lorentzian metrics? Seems like a natural choice. This is not necessarily different than what I just said, because after all, if you take Euclidean metrics and you complexify them, consider metrics that are Euclidean, but with complex coefficients, well, some of them are real Lorentzian metrics. So this actually fits into the old paradigm. It is a contour in the space of Euclidean metrics. It's just one that has a different way of looking at it. Okay. So what I would sell you on if I had another 2 hours to give a talk is that there's a very interesting story here. Well, first of all, there's an interesting, this seems like this is a nice set of words, but there's an interesting tension with the story I just told about wanting to understand processes that involve topology chain. Because in particular, if I study spacetimes that start off with, as I drew in my little example, one connected component and then split into two, then there really is no useful smooth Lorentzian signature metric on such spacetimes at all. Because funny things happen where the spacetime splits. So how could I possibly hope to merge the two? Well, luckily, I didn't really have to, because back in 1995, Jorma Loko and Raphael Sorkin wrote a paper that I really didn't understand at all at the time, but I now just love. Okay. And what they did is, in the language, well, they did it in 1+1 dimensions, but you can generalize it in a certain way. What they did is to look at a certain class of metrics, and I will describe them as being Lorentzian signature metrics, except that there's a certain sort of codimension 2 set on which they are singular and not smooth. And this is exactly the place where this Lorentzian structure has to break down. So it's not a well-defined Lorentzian metric, it's singular. But nevertheless, they showed that there was a way of defining the Einstein-Hilbert action functional on metrics that had this kind of singularity. And that would allow us to talk about universes that, for example, split in half or undergo other kinds of topology change. And their way of defining the value of the Einstein-Hilbert action was that the class of singularities being used is kind of like a Lorentzian analog of a conical singularity. And in conical singularities, we know that we can kind of round them off and then we take a nice limit where they become a cone. It turns out that, as I said, topology prevents one from smoothing out these singularities with Lorentzian metrics. But you can smooth them out if you allow your metric to be complex. And then you get a kind of a nice answer. So the message that I want to convey, and that I'm not going to have time to actually sell, is that if you take their prescription and use it to define an action on Lorentzian signature metrics with codimension 2 singularities, it allows you to talk about the action for, quote, Lorentzian signature topology changing configurations. And it allows you to write down at least a formal Lorentzian path integral. And if you take it at least somewhat seriously, it appears to reproduce all the things that have been called successes of the Euclidean path integral without introducing the conformal factor problem. Furthermore, it does even better. It turns out that, as I said, in the Euclidean story, people have usually used the semi-classical approach where they find a saddle here and a saddle there and a saddle there. And in many cases, they can say, I like that saddle, I don't like this one, and they can get some physical result they like. But in more complicated settings, where the various saddles that they identify are so complex, meaning that the actual metrics are not Euclidean or Lorentzian, but they're really complex in various complicated ways, it's a priori not obvious whether they should like that one or that one or that one. Applying this kind of approach to those contexts seems to give an answer for which saddles you should keep, which seems to make a lot of physical sense from various perspectives that unfortunately I'm not going to have much time to explain. So that's really the punchline. And again, if I had several more hours, I'd say a lot more. Did that say 2 minutes or 0?
It would be 0, but let's say this one.
Okay. So as I said, if there's several hours, I would explain various more additional details. Oh, I want to show this slide because there's some set of interesting references, which I have this slide really just because it's going to be archived someplace and probably put up on a website. People can look at it, but it gives me an excuse to mention that this connects to Ted's work with Bianca and Jose. And I guess I need to talk to Ted about whether he thinks that their work is doing exactly what we're doing or just has strong overlap with it, but has some of the same results that you can also use. In particular, you can use this kind of technique to argue that it reproduces via the path integral the entropy of de Sitter space. It's an interesting thing. All right, so, right. This is my story. I was trying to explain the idea that defining the Lorentz signature path integral by integrating over real Lorentzian metrics, quote, with Lorentzian conical defects provides a somewhat unambiguous starting point to analyze which saddle points of the path integral are relevant, which classical complex solutions plausibly encode actual useful tunneling phenomena in quantum gravity. And here are a few things you could apply it to. It turns out it gives interesting and subtle results for things like analyzing space-time wormholes and contributions from what are known as shifted black holes. Those are all just technical words. Interesting things we'd like to do in the future are apply it to, for example, suggestions. There have been interesting suggestions that some interesting quantum corrections are associated with not just the usual Euclidean geometries, but with Euclidean geometries that have the overall wrong sign. So for example, that you might associate corrections to de Sitter physics with hyperbolic geometries, but which have negative definite metrics, so that the Ricci scalar is positive. Okay, but if you followed all those signs, those are interesting suggestions. I claim we have a framework in which it is natural to, in which we can decide whether those proposals are correct, meaning consistent with our framework. We can at least begin to evaluate that proposal in a well-defined way. It's an interesting thing to do. And I'd love to think more about quantum corrections and various other things. Oh, here's a very interesting question that I also like to understand better, that I want to relate Lorentzian prescriptions to Euclidean prescriptions. But it's an interesting question. In a space-time with various kinds of topology, let me start with the Euclidean space-time. I could imagine corresponding Lorentzian spacetimes where the time direction is sort of this way, or Lorentzian spacetimes the time direction is kind of this way. A priori, it's not at all obvious that those two would define the same integration contour for my path integral. I'd like to understand if they do. I'm not sure it's a problem if they don't. It's just a matter of understanding what class, maybe that's more in the weeds I need to get into. But I think it's an interesting question of There are lots of things you might try to do from a Euclidean approach, and the answer to which Euclidean or complex saddles contribute might possibly be dependent on the exact physical question you're asking, which might be obscured in a Euclidean approach. All right, I think I'm wandering off into the weeds away from things I actually discussed in the talk, so I'm going to finish, but thank you for your attention and patience.
We have time for a couple of questions.
Sorry.
Is there a principle that selects the specific regulator for the singularity as natural?
Principle. So in the Locus-Orchid paper, the idea is that okay, what makes a regulator natural? Usually we'd like to try to figure out how to smooth out singularities and take a limit. In the context of that paper, the singularities cannot be regulated in a purely Lorentzian way. So you have to do something complex. And then up to one choice of sign, the argument is that the way in which you make it complex actually doesn't matter. The details of the regulator are not important. Just as in the same way, when you take a cone in Euclidean signature, you can round it off in more or less any way and you get the same answer. So does that answer your question?
I think that gets at it. I mean, one property that I would certainly like from regulator is that it, to some extent, your answer is independent of the choice of regulator.
Yes.
Like with UV cutoffs.
Yes.
But is there anything natural about the complexification? If you didn't know about the Euclidean path, that you were trying to reproduce results from the Euclidean path integral in the first place, and if you were just considering the Lorentzian path integral from the outset, is there, would you consider complexifying the metric to be a natural thing to do?
Well, how would you feel if I said that instead of complexifying it, I wanted to replace the continuum calculation with Reggie calculus?
Okay. Does it give the same answer?
Yeah.
Okay.
In Reggie calculus, I think this is especially natural. Whether it's natural, because Reggie calculus has codimensions 2 singularities all over. And this is the way that you would naturally treat it in Reggie calculus. In Reggie calculus, you certainly don't mind codimension 2 time-like singularities, which don't really affect the causal structure. They're just usual Euclidean conical deficits in space. It's therefore natural in Euclidean in Reggie calculus to also consider what you might call space-like codimension 2 singularities, and to define the action there by just the analytic continuation.
Okay.
That gives the same answer.
I see.
So perhaps you like that answer.
Okay. Thank you.
Okay. There is Ted that wants to.
Yeah, I'm wondering about topology change in this, with this prescription. So many years ago, like more than 35, I think, Witten considered Euclidean quantum gravity in 3 dimensions, formulation of topology changing amplitudes. I never really liked it because it was Euclidean. I didn't know whether there was an underlying unitary theory, whether it was really quantum mechanics he was doing. But you're suggesting, I mean, let's just redo what he did in 3-dimensional quantum gravity with your prescription for defining actions.
Yeah.
Do you
Well,
get, I could see that topologically you could allow topology change, but do you get amplitudes that define a unitary transition amplitude between different topologies? In other words, can it be interpreted quantum mechanically and in a proper sense?
We should think carefully about what we mean by unitarity and so forth. But bottom line is, we should look back at what Witten actually did. But what I will say is that all the Euclidean calculations that I know of that are consistent with things like unitarity, and which we think are physically appropriate, that we've tried to reproduce, we do reproduce. So I think the answer is yes, but we should talk about the details and what's there, and maybe there's something else that's especially interesting to do.
In the scattering case, he didn't have the same kind of anchors that would give confidence that it was consistent with unitarity as you might have in other settings.
Okay, so he had some prescription, but you're saying he didn't know if that was really unitary.
That was my impression, yeah.
Yeah, so maybe we can do better. Yeah, quite possibly.
Okay, we have one last question.
You said going beyond mini superspace was this discussion on the context of mini superspace.
Oh, you're reading my
Yeah.
So the way that we in practice, so I have some general sort of proposal for the path integral. The way that we actually study concrete models is by a kind of mini superspace approximation. Kind of mini superspace, where we will, the path integral is some, in principle, infinite dimensional integral. We pick out a certain finite number of degrees of freedom that we think are physically particularly important. We imagine doing the path integral by first holding those particular finite set of parameters fixed, not integrating over them yet, and integrating, quote, integrating over everything else by doing a cheap saddle point approximation, meaning we find some saddles and say, I like that one, I don't like that one. Usually we do it in a way that we hope we like all the ones that come up. And then we carefully study the remaining finite dimensional integral. That's what we actually do in practice. And so obviously that's a limitation, and it'd be nice to talk about the full infinite dimensional system, at least if you can treat the other infinite number of modes perturbatively or in some linearized approximation.
Okay. We are about time. Okay. Okay, perfect. So thanks again, the speaker.
Yep.
Uh,
I think